Buried in BMW's announcement about their overhauled Munich plant is a rather curious number. To build the body of their upcoming Neue Klasse vehicles, the engineers capped the manufacturing line at exactly 5 joining processes. That doesn't mean the car only has 5 spots where pieces connect. It means the entire assembly relies on only 5 kinds of joints. BMW treated this limit as a formal design brief, a decision running in the exact opposite direction of everything currently happening in material science. Establishing a mathematical ceiling during the concept phase dictates the engineering of every car component. Right now, the dominant logic in manufacturing goes like this. If you can put a specialized material in one specific spot and improve performance, you should. The case for mixing materials is overwhelming. This chart compares the carbon footprint of traditional carbon fiber to a new flax composite. Using flax on a BMW concept car drops carbon costs 85%. Transition to a hybrid landing leg cross-section. Placing carbon fiber where tension runs cuts mass by 30%. Push this logic far enough and the mixture becomes the core function. Researchers recently built a thermal cloak using 3D printed aluminum to conduct heat along exact paths, while a heat-resisting polymer called PDMS blocks it. Neither material does the job alone. The junction between these materials is the device. Adding specialized substances seems mathematically perfect on paper, masking a physical trade-off that rarely makes the press release. Every new high-performance material added to a design makes the overall product worse. 2 materials different enough to be worth combining are also different enough to be inherently hostile to each other. You cannot weld flax directly to steel. At the microscopic level, they constantly fight. They have different stiffness profiles, distinct surface chemistries, and different rates of thermal expansion, constantly trying to pull away from one another under stress. To force them to hold together, every single pairing requires a new joining technology, a unique adhesive, a specific fastener, or a complex hybrid process. And each of those brings an isolated qualification program, a new line of tooling, and entirely new repair procedures. What looks like a sleek, optimized structure on the outside is actually a fragile web of unproven adhesives and multiplying failure modes on the inside. Eventually, the product reaches the end of its life, and all those bonds have to be undone by a recycler who wasn't in the room when you designed it. This is where the economics of mixed materials collapse. A bonded, multi-material assembly is almost always economically unrecyclable, not because we don't want the raw elements back, but because the operational cost of physically or chemically prying them apart is higher than the value of the recovered materials themselves. Even that high-tech, carbon-saving flax composite has a bleak final destination. Its primary end-of-life route is waste to energy, meaning it just gets incinerated. When you are burning advanced composites to get rid of them, corporate claims of circularity across the value chain look like a polite fiction masking a failure to recover the materials. Which brings us back to BMW's body shop. There is no magic to the number 5. What matters is the deliberate, early choice to establish a strict ceiling in the first place. Once that limit is set, it has to be defended against every subsequent engineer who arrives with a mathematically sound, well-intentioned reason to add a 6th material. And their arguments will be good, backed by genuine mass or carbon savings. Yielding to those arguments invites costs that never show up on the initial blueprint. Instead, they surface years later, in the repair network, in warranty payouts, and eventually in a recycler shredder. Material count cannot be treated as a minor detail you figure out during engineering. It is an architectural boundary that has to be established on day 1. For a masterclass in this restraint, look at the Panton chair. It has survived for 60 years because it was designed as a single, continuous piece of plastic. There is quite literally nothing inside it to come apart. This philosophy scales to massive industrial objects. When Airbus flight tests high-span wings for their next-generation aircraft, the span drives the structure so directly that the material strategy and the architecture function as a single, inseparable system. They don't fight each other. Deciding it late guarantees you inherit whatever accumulated. Deciding it first forces discipline. Design decisions are cheap at the concept stage, but they cannot be revisited once the tooling is cut.